Hello and welcome back to a new video in my C++ tutorial series here on the Ludwig Fusel channel. Today we're going to talk about the holy big three. The big three is a very important concept in programming in general, but especially in C++ when it comes to resource management and writing your own objects. And the big three is like the bare minimum that you should provide if you are writing a object. If you're writing an object in C++, the big three are important. It's really important to follow them, and if you don't follow them, bad things can happen. And actually, what we have already experienced is that bad things happen if we don't follow them, because we have, until yet, not heard about the big three and didn't even follow the big three because we were not aware that they are there. However, they are there. This concept is there, and if we violate it, or if we are we are currently violating the big three, but currently the way we use it, we don't see it. However, we already saw it, that if we violate, then bad things happen. If I would remove the reference from here again, I'm going to show you what happens if you don't follow big three. 5 and 5, and we have the crash here. Breakpoint instruction, blah, 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 heap corrupted, whatever. So you can see something doesn't work, and this doesn't work because we haven't followed the big three. And initially, if you are seeing issues like that, you might be really spoiled and you have no idea what's going on. You need to work yourself up through the call stack and really need to know already what's going on to really find out why the termination of your main function fails. And yeah, that's why I am here, and that's why we are talking about this, the big three. Alright, what are the big three? The big three are resource management of your object, or generally your data. You can see that we are using a pointer values inside of our function precacher. If we would not have used the heap at all, we wouldn't have an issue. Actually, this issue that we got, I told you why this is happening. This is happening because we are deleting the values twice. We are twice deleting the same pointer because we are just getting a plain copy of the actual value of the pointer, but not the data to which the pointer is pointing to. Talked about why this is happening. We talked about why it's not happening differently. We talked about all of that. However, this is like the problem, and this is like the issue that we have, and this is like, as soon as you have something like that, why the big three are important. And in general, I'm even that far. I'm always actually doing the big five on every class that I implement. Big five is going to be the topic of the next video. Today just big three because we're starting small. And it's important for resource management. Okay, so big three is actually not even too far away from you. In general, you could already come up with what the big three are. Well, I told you that it is about resource management and making sure that your objects are safe. And you can see that our object is currently partial safe. Why is our object partial safe? Well, because we don't need to call release ourselves. If we need to call release ourselves, then we wouldn't be safe at all. Then we would violate all three things of the big three. But currently, release is called automatically, which is already fulfilling one criteria of the big three. And this one criteria is implementing a destructor. So big three is all about memory management, object lifetime, and all of that stuff. And actually, the big three specify like three criteria. And the one criteria it specifies is destructors. Every class that you implement that is handling something with resource management should have a destructor that cleans up the resources automatically. So the idea here is that if something is still in here, what is being checked by release, so release checks if the value pointer is still set, and then it deletes it and sets this to a null pointer so that it properly is cleaned up. And this is in general what the destructor shall do. The destructor shall take a look at all of the values that are like critical and evaluate if they need to be released. If you have like a DirectX object, you want to call release on it. If you have a Microsoft object, call release on it, common Microsoft stuff in general. If you have a pointer that you have allocated in your own class that you are owning, we are talking about ownership of memory. In this case, we allocated this, and if you're allocating something inside of a function and you're just storing it internally, you're going to own it, and so you are also responsible for deleting it. And the destructor shall make sure that every resources that are like owned by an object shall be freed. And we already have done this, so we already archived 1/3 of the big three without even knowing it. However, the big three, as the name suggests, is built out of three criteria, and we have just talked about one. And the other twos are not even that far to come up with. Well, what we have seen here is down there inside of the print PC, if we had the ampersand here, so we are kind of like creating a reference, which is fairly similar to a pointer, everything worked. Well, it worked because we have just getted a reference to that object. We have not copied it. But if we wouldn't have that reference here, we create a copy of an object. And the copy of the object is going to be a plain copy, which is done with like the default algorithm of C++. And the default algorithm of C++ is just going to copy everything inside of the class without any brain. Of course, as I already told you, if you're having an object in an object and it's copying that one, it's of course tries to copy this object as intelligent as possible. So it is in many cases fine to have it in like there, but as soon as you have like raw data that needs special attention, especially like this values pointer is managed by you. You need to manually call release and manually need to manage its lifetime. So copying this pointer around is not a good idea because it's violating that. If you copy this pointer around, it's owned by two objects, and two objects owning it is not good because both of them are gonna be destructed. And if the second one is destructed, the first one already struck and already deleted the pointer, and the second one is gonna go into the error that we just had. So it's not a good thing. And now I'm gonna ask you, what might be another criteria of the big three? You are right, it is copying the data around. And actually copying in C++ is done in two ways. So actually copying is 2 out of 3 of the big three. And if your math is correct and you take 1/3 plus 2/3, you should be at 1, and you should have completely fulfilled the big three if you are doing copying correct. And that is exactly how it is. So the only thing left to kind of like understand the big three is to understand how copying works. Now, copying in C++ can be done in 2 ways. Well, we currently just have occurred one way of doing copies. It is the idea of creating a new object based on an existing one. So this one is defining a new object, a constant function precacher called PC, and this one shall be copied from an existing object called PC here as well. So what it is doing, it is creating a new object out of an existing one. This is like one way of creating a copy in a programming language. However, you could also do this differently. You could create the SPC, the second PC, which takes a 10 and a 3, and also performs its copies on F. So you could have that SPC. That SPC might compute something, and after that you want to assign the PC to the FPC. This is also a kind of copy that can be done in C++. So here you are taking an existing object SPC and you are overwriting it with the data of PC. So in general, what you are doing is you're taking an existing object and overwriting it with another existing object. So 2 existing objects, while when calling print PC, we created a new one out of an already existing one. And you can see that both of them work. Both of them are implemented by default, and both of them are implemented the same way. Both of them by default just copying the data over, just a simple plain MemCopy. And in our case, I told you this doesn't work. So what we need to do is we need to come up with a way to handle both of them. Now, actually, the big three doesn't really tell you that you need to do this. The big three just says that you need to manage these three. You need to manage destructing and both ways of copying objects. However, the big three is not limiting you to saying, no, copy is not going to be supported. So what you can actually do is you can actually say, all right, then I don't want to support copying the objects around. And this is something that we want to do here now as a beginning step to actually see how the functions look, the copy functions, and how we're going to do them. And I already spoiled you, for copying, of course, we're going to write functions. Well, because everything in C++ is just done with dumb functions that are called automatically. All right, so how do we create a copy of an object? We have 2 ways for that. We have the way where we are kind of like creating a new object out of an existing one, and another one where we are assigning an existing over to an existing object. So 2 existing objects, one of them is assigned by the other one. So the one is copied and the other one is overwritten. Now let's start with the easy one. The easy one is creating a new object out of an existing one. And well, maybe you already have an idea. Do you maybe have an idea? Maybe pause and maybe think about this. I'm going to spoil you in 3, 2, 1. Okay, so how do we create a copy of an existing, or how do we create a new object out of an existing one? Well, we're just going to write a constructor for this. So in general, the idea is that you create a constructor which takes a reference of any other object. But it's not any just plain reference, it's actually a so-called const reference. It's a const reference one because a copy shall never modify the other object. So if we are taking a sheet of paper and you're copying it, it's not going to modify the original sheet sheet of paper. So the idea here is that you are taking a const reference of a other object into that constructor, and then this shall create a copy. And now you could add the implementation to that and do some fancy copying, or you could just say delete and say, all right, I don't want to support deletion of the object. Now you would actually think that if I scroll down here, it will no longer be able to create an object here, which is completely right. You can see we can no longer create it here by calling print PC. We don't have a reference here, we just have PC here, and it's red underlined, and if I hover over that, function precacher of const precacher reference other declared at line 13 cannot be referenced. It's a deleted function, so everything worked out as it should be. So it's a deleted function and everything is good. Now if I would add the ampersand above here again, so if I add the ampersand here, you can see it's gonna still work because references are still allowed. References are not copying data, they are just like pointers, and this would be now available again. So if somebody forgets to actually write their code correct, they're gonna get an error here, and we can say, all right, we're gonna delete it and everything is good. Alright, so now let's talk about this assignment. This assignment is a special assignment. Why is that a special assignment? Well, because C++ is kind of like a bit of a interesting language. I could add this PPC object, and what I can actually do is I can do stuff like that. SPC equals PC equals PPC. We can do something like that, and this is like really basically PC is assigned by PPC and then SPC is assigned by PC. So really what we are doing is we are doing a hell of a lot of overriding. So what you could do is like PP equals something like that one here. And if I would now quickly comment this out and show you what would happen with that code is, let's quickly go into here. 5 and 5. So in general, what's happening here is that we have this like SPC, and this FPC is gonna get a computation now here, and everything is good. And you can see that like the PC is the already existing one, the PPC is an empty one, and then SPC is some other object. And if I would now go through this step by step by F11, you can actually see that at the end, all three of them are gonna be equal to the PC object. So really what's happening is it's going from right to left. So the first step, what it is doing, it is overwriting PPC with the values of PC, and then it's overwriting SPC with the values of PPC. So they can be kind of like chained together. And this is something that's nice in the language, because especially when you are initializing data, you can do something like int width and height, and you can do something like width equals height equals 0, which is really nice because it's all like in one single line. So if you have like some function void clear, you can easily just do like a width equals height equals 0, and it's looking quite nice. And yeah, I mean, like, I personally don't tend to use the syntax because it's rather confusing. But the language supports that, and that's the power of the language. It's working from right to left in this case. And since the language can do this, this is what makes our life on actually like modifying this copying way harder. Okay, so let's first talk about what's really happening if we are doing it. Let's quickly remove the PPC because we don't need it, and just make the assignment here to PC here. So remember back in the days when I explained cout. Cout is an object, this is an operator, and this is another object or a variable. It's a const char pointer. You can also see a const char pointer as an object with just one member. So I'm just going to talk about objects here in general. So you have an object on the left, you have an object on the right, and you have an operator in between. And that's the same thing what's happening here. You have an object on the left, you have an object on the right, and you have an operator in between. And we need now some way to implement this. And this is now already going inside of operator overloading, because operator overloading is the base of actually assigning or copy assignments. So assigning the value here, copying the objects by assigning it, but we need to understand this for the big three. Now, what we basically need to do, we need to again write a function. Now, up here in our code, we need to somewhere, I tend to write them always here after the destructor. I always have this like at constructors, destructors, assignment, functions, and later on operators, but that's just how I do it. You have to write a special function. Now, as I told you, you can chain them together. So if you would chain them together, it works similar than what we talked about on cout. Cout, if we would like cout some a, and B. In cout, it works the other way around because this is the shift operator, and the shift operator operates from left to right, which is completely different than assignment. Assignment from right to left, cout from left to right. This always depends on the operator. And what this is in general doing, it is calling a function with cout and the A. And this function is kind of like operated, and the return value of that function is fed to the operator again with the B. So in order that cout is actually able to be chained together, cout needs to have an operator defined that takes cout and a const char pointer and returns a reference to itself. So a reference to a object of cout, so that this can be called infinitely. So that in general, if that one is evaluated, that function cout, it's calling the operator with the A character in, and it needs to return the object cout again so that it works the second time when you're going inside of B. And this is similar working with you're doing the assignment. So if you're doing assignment, let's just call this, let's just say PC equals SPC, SPC equals PC. So what needs to happen here is that this operation here, this assignment operation, needs to return something that can be interpreted with the assignment again. So the PC equals SPC needs to return something which allows SPC equals to be PC. Again, it's still the return value of that one here. It's the return value that we get, which is fed into the SPC function. But you kind of like get the point. You need something as a return value. And the return value needs to be the object itself. However, it cannot be the object itself. It can't be a copy, right? Because we don't want to do a copy. We just want to operate like with the addresses, the references to this object. And again, pointers doesn't make sense, because if we would have a pointer, we always need to like do something like this, like SPC. And we would need to put brackets around this. And we need to dereference that, so we do this, or we need to write all functions so that they take pointers, and this really doesn't make sense. So in general, what we do is we always work with references. Always do this. We have this above here in the copy constructor. We already had it here as a reference, so we're going to do it as a reference as well. Now what we basically want to do, we want to have, I'm just going to put white in here, we want to have like a function operator here, operator assign, something like that. That name is just arbitrary, that's not going to work. And what we want to do here in general is we want to get a reference to a function precacher in here. This makes sense because we want to have it here, we want to have another one. And what we want to do is we want to return something that is doing the same, is being able to do the same thing again. So if we want to return something, we actually want to return a function precacher reference. So we want to return a reference to the result of that computation. Now this is actually not a const reference, because the assignment is like done from right to left, and if you're doing the assignment from right to left, so you're kind of like assigning SPC to PC. You want to then have the result of a modifiable object, and the modifiable object is the PC on the left. That needs to be modifiable. This is not allowed to be const, because if it would be const, it's not allowed to be assigned. So we want to actually return the reference to PC, which is an object without a const. So this is why above there we don't have the const reference here. We just have the normal reference. So we want to have a function that kind of looks like that. And for now, we just want to delete it, which is going to make sense in the syntax that we write it. However, we want to have something that returns a function precacher reference. It takes a reference to another one, and it kind of like implements this operator. Now, if you can see, if I do this like that, of course, it's not going to work. You can see that we don't get red underlines. Everything still works. Again, above here, if it's deleted, we have red underlines. It doesn't work. But this one here, you can see it still works. So our name is not right. And now you need to just know how it works. Well, actually, if you want to overload an operator on C++, you're going to type the word operator. And now you can see that if I type in operator, it's getting blue. So this is kind of like a keyword of the language. Now you can see that we have a red underline, and it might say something, expected an operator. And it's exactly telling us what we have done wrong. It has expected an operator. So if we want to overload an operator, we need to tell it which operator do we want to overload. And this is actually quite simple. What operator do we want to overload? We want to overload assign. And you can see if I write that, the operator itself gets a different color, and if I hover over that, you can actually see that it's like been recognized correctly and decorated somehow. And you can see that like the function precacher reference, operator assign, it kind of looks good. And this is exactly how you overload operators. So by taking the keyword operator and the actual operator that you want to modify as an assignment, you actually want to take this like that. So that the language understands what you want to do. The compiler understands it. And this is exactly how assignment works. This is how the assignment operator looks like. And if we delete this, it is deleted and it shall no longer work. If I scroll down here, I might give it a few times to refresh. You can see that we're going to get red underlines here, and it's going to tell us function blah 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 cannot be referenced. It's a deleted function. So you can see that our assignment is now no longer working, which is exactly what I have wanted to do. Alright, so this is in general how you do the big three. And we could end here and say, alright, good, we have deleted the functions. The big three just implies that we need to do destructing, and we need to handle assignment. And if we don't want to be able to assign, we can delete them. And big three is satisfied and everything is good. However, I personally don't like the idea of not supporting these operators. I actually do want to support them. Why do I want to support them? Well, because it makes sense to support them, right? We might want to store this somehow. So we might have a function precacher stored like 5, or stored, yeah, let's just call it stored 5, because we always enter 5 in the console, and I might want to, after I have computed them, store them. I might want to say stored 5 equals PC. This might be something that I want to do. And to allow this, I need to implement the operators, right? Of course, I could like try to get these values and compute them again, but no, that's not the idea. I don't want to compute them again. I just want to copy them over. How do I gonna do this? Well, I just need to implement these assignments. So as you can see, I previously deleted it. Now I'm just not going to delete the constructor, and I'm going to write an implementation for that. How does the implementation look like? Well, now since I have a custom copy operator defined, I also need to do all my coding here. So as I scroll down here, you can see that we have multiple members that we need to deal about. We have these 4 members, and we need to deal with each of them. By default, with the constructor, it's just going to initialize them to the default values, so they are already set. As soon as the constructor is called, they are already restored, and we are now left to actually assign a value that makes sense. And I always tend to start with the simple ones, so for example the x. I can just copy them over by saying x equals other.x. Now actually x was a private variable, so in general if we would be in our main function and I would try to access PCX, we can't write it, we can't assign it. This doesn't work because it is private and not accessible. However, these access modifiers are not applying inside the class. So inside the class, I can do this. I can, of course, get access to these members because I'm inside the class. The class knows how it's built internally, and it has access to these. It has access over object boundaries. Still on the same level, because we are inside the class, we can access them, but this is like the access modifiers are not operating on a per object base, operating on a per class base. So what I want to do is I want to assign x, I want to assign count, and I want to assign the function. So by doing that, I have copied all the metadata that I need to call compute again to compute my data. And if I would do this like that, you can see I'm going to compute the data again. Everything should work. And if I scroll down here, you can actually see that both of these implementations are now valid. Why are both of the implementations valid? Well, because this one is going to be turned into a copy construct. Because we are directly assigning it, there are no other things done. If I would create the object first and then say stored 5 equals, this needs to be done like that. If I would do this like that, it wouldn't work, because now it would call the default constructor and then it would try to assign this. However, if I do a direct assign here, then it's going to work, because it's going to say, all right, you're going to directly assign this. Okay, I'm going to call copy construct. So just because there's an equal doesn't mean that you're calling an equal. And maybe even if I hover over that, I might be able to see it. No, because it's not even like decorating this operator, because it's directly turned into the copy construct. So this is like similar than if I would have called something like that. This is completely the same. And I'm just gonna start 5. I'm just going to quickly do this like that so they can see that this doesn't work, and I'm going to comment this out until we get it working. Alright, so what we could do is we could do it like that. Still remember, we have removed the reference here, and we can start it. Let's see what we got, and I say 5 and 5, and you can see that we are getting the values and everything seems legit. I could go inside of my PC print, press start here, and see what we got. And you can see inside of my PC print, I have the PC, and the PC values are stored at 128B0. If I go one level up, you can see that inside of that PC, the values are at 12BA0, which is a different pointer value. So you can actually see that we have two versions of that existing. We have the version existing in the main with the pointer pointing to 12BA0, and we have the version in the print PC with the pointer pointing to 125B0. So two objects, two times the memory, and yeah, everything handled correctly. Now, this is of course not very efficient because we now have two times the memory wasted, even though we would only need it once. So in general, we want to have a reference there because we don't want to copy the data. But this is not the idea of that video. The idea of that video today is to show you how we can do it with copy and without like paying attention. But in general, if you don't really want to have a copy, if you're just a reference is just enough, then you always want to have references, of course. But we're gonna show to you that this is way more involving if you're doing a copy later on when we are done with coding. But again, the idea here is that you're going to get a full copy and you're going to get a complete deep copy by doing it again. Now, are we really doing a copy? Well, actually, we are not doing a copy. We are calling compute again. This is something that I don't like and something that I want to avoid here, because computing again might be quite extensive. You don't know what the function f is doing. The function f might be 500 lines trying to get some data over the internet, random number generation. It might do something like that, or the function f might be like a random number function, as I already suggested. A random number function that always returns something differently because it's like dependent on a random value. And if you're copying something and you are depending your f on random values, you're going to get each time you're going to copy the data, you are going to get new values. And that's something that you want to completely avoid. You want to avoid additional computations, and you want to avoid that the function f might do different things when called multiple times if it's not deterministic. So this is not a good idea to call compute again. We rather want to completely copy the data over. How do we copy the data over? Well, first we need to check if the data is even there. So if we have a pointer inside the other, so if the pointer value is valid, we now want to copy it over. We need to copy this over by first allocating our array. So we need to create a new int32t here, the size of it. We could take our own count, but what I personally like to do inside of the copy ones, I always like to stick to like the others value, because they have already been copied, but still kind of like, for me, my object is not initialized properly. This is why I tend to fall back on the values from the other class, because the values from the other class are done. For example, if I later on move this one down and I have my own values or my own count in here, this might fail. This is why I personally tend to always have like others count in here. Would I really recommend. Now, after allocating this, we of course need to check if it has been allocated. If we got an error there, we don't want to of course continue. And now we can do a normal memcopy, and memcopy is inside of cstdlib. I don't think that we have it. cstdlib here as well, and inside of cstdlib we want to do a memcopy, so I want to do an std memcpi. To do a memcopy, the destination is going to be now my values array. I'm going to copy from the other values, and I'm going to copy the size of int32t times the others count, because still I'm not trusting that my count is already correct. And now the idea of that code is that we have a full copy of the values now inside of my class. Let's test it out if it's still doing the same thing. I'm going to quickly see if it still does the same thing. What's going on? I'm not getting input values in the console. Let's restart this. I think I screwed something up. Still the reference is not in here. Let's start this now. Okay, enter the value 5 and 5, and you can see that we are still getting the same data. And what we actually have done is we have actually copied this. We can verify this by making a few breakpoints in the code and actually seeing what's going on, or we could instrumentalize this. Let's instrumentalize this. This looks a bit better and is a bit, I think, easier for you to understand. All right, so let's say an stdc out, allocated values, computing or crunching numbers. So we are crunching numbers for computing that. And what I also want to echo out is if something gets destroyed. So let's also echo out that. So stdc out, released values, data gone. So the data is gone. And what I also want to do now is inside of the copy constructor, I want to also call that I'm copying. So stdc out, copying from other values to new allocated values. Let's do an std handle here as well so that we can see how the memory lifetime works. Did I make this already good here? No, there's one too much, and this is all good. And now if we would run this, we should also get some debug output that tells us how the data is computed and done. So you can actually see that we allocated 29E0. It was crunching the numbers. Then you can see that it copied from 29E0 to the new allocated 2513. So 29E0 copied to 2430, copied the data over, and then it released 250 data gone and 29E0 data gone. So first the copy was destroyed because we exited the function, and then the original data was destroyed. So you can see really what's going on here is, oh no, I closed the console, I didn't want that. You kind of like saw that we have once allocated and crunched the numbers, then we have done an actual copy, and then we have 2 times released the data. So we have still 2 versions of that memory available, but we have one time computed them, and the other time we have just plainly copied them, which is exactly what we want to do if we are doing a copy constructor. We don't want to recompute them. It's not really a good idea. So you can see this one works quite fine. Now the only thing left to do is to make that one work. Store 5 equals PC. Now, this one is actually a bit more involving because we need to have a few more things in mind. So let's try to implement this the naive way. So first of all, this function requires a, of course it's not going to be deleted now again, it's just going to get implementation. Now, of course this function requires a return value. What are we going to returning? We're going to, as I told you previously, we're going to return a reference to ourselves. How do we get a reference to ourselves? Well, we have a this pointer. The this pointer is a pointer to the current object. So we could try to return this. But you're going to see that this does not work because this pointer is a pointer. But you can see it's a function precacher pointer, but it's not a function precacher reference. To get this to a reference, we need to dereference it and everything is good. If we dereference it, we can return it and we can return the reference to ourselves. Alright, so now we are at the assignment operator. How would we implement the assignment operator? Well, first of all, we would need to copy all the plain data over. So do something similar than what we have done here, that one, right? So let's copy that one over. Okay, so let's paste them in here and we are good. Now we also need to copy over the value. So let's also take that one, copy it, paste it in here, and we are good, right? Are we good? No, we are not good, because we now have a memory leak inside of our code. Where is the memory leak? I'm going to show to you where the memory leak is. I'm going to show you the memory leak by going down to stored 5 and giving it the x, count twice, and the function f again. And then I'm going to say stored 5 compute. And if I do this like that, you're going to see where the issue arises. Let's press a 5 and show you what's going on. Okay, so let's do 5 and 5 and show you what's going on. Okay, so what we have done is we have allocated 28. Let's maybe keep track of all the addresses we allocated. So let's copy them over. Let's open up an editor window. Notepad. It's, I know it's called Notepad, but come on. Notepad, there we go. So that one, let's make this a bit bigger so you can see this a bit bigger. These are like all of our arrays. Let's keep track of all of our arrays. So we have that array that has been allocated here. So let's maybe add something like A for allocated so that we know what's going on. So allocated that array, we crunched the numbers, and then we were copying that to the new allocated A0. Okay, so the new allocated one is called A0. So, or not called A0, I always tend to just name the ones behind there, but this is like the new allocated one. Alright, so this one has been allocated. Now you can see that we are doing some numbers and we are releasing the A0 one. So the 23, A0 has been released. So allocated and released. Good. Now we continue on with our main function. We allocated the EFFZ17, crunching numbers, so we have allocated that array. Here, allocated, everything is good, crunching number, something is in here. Now we are copying from 28 to newly allocated 0, 20, D0, so we are copying to that one. And this has been new allocated and everything is good. And we are copying to that. Now you can see that directly that one is released. So 20D0 is released. So okay, 20D0, this one has been released. And we're going to continue on with our code, and 2800 has been released. So the first one has been released. And then our code terminates, and we are left with a memory leak. The memory leak is the third one that has been allocated, the FZ70 or FC70 as I like to call them. So one of them has been allocated but never been released. Why has it not been released? Well, because we are on a copy assign. If we are on a copy assign, that one here, copy assign, or yeah, like that, copy assignment, we are writing two values. However, values can already have a value in here. So what we really want to call, before we even do all of that stuff, we want to call the release function. So we want to make sure that the old pointers get released before we then do our copying and doing the other values. So we want to make sure we first release it, and we then want to construct our object. And if we do it like that, we can quickly try this out again. We should in total get now, as I told you, we previously had 4 allocations, but only 3 releases. So to verify that everything works now, we just need to count that we have 4 releases. So release, 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 and now we can see that we have the proper number of releases, and this means that our code is now working and everything is good. However, it might not. Why does it might not be good? Well, because people are evil. People are really, really evil, and people could come up and say something like PC equals PC equals PC, PC equals PC, something like that, right? Is it a good idea to do it? Well, the language doesn't disallow us to do that. And our code, okay, actually, okay, the compiler has optimized this away. So PC equals PC, it's called self-assign, and it seems that the compiler has just optimized this away, but you cannot be always sure that it does that. So self-assignment is something that now I try, of course I try to show something why you would need to do something, and of course it doesn't work because the compiler is smart enough. However, this might be an issue. Self-assignment is an issue that can occur in theory, and what we want to do is we want to actually check for self-assignment. So inside of that function, before we do all of that, we actually want to make sure that this is not equal to the address of other, so that we are not doing self-assignment, right? So this is this pointer, address of the other object, so compared to addresses, and if they are not the same, so this is not equal to the address of the other, so current address not equal to the other's address, then we're going to do an assign. This is checking for self-assignment. I wasn't able to reproduce that, but there are cases in which this might work, and if you're doing something by accident, then bad things can happen, and this one is catching this for sure. And again, the code itself is not going to change by modifying that code. Okay, so really what you want to do is, if you want to copy assign, is what we are really doing here is we are calling the destructor and we are calling the constructor. And this is what I personally don't like. I personally don't like code duplication. This one is the exact same code than here in the constructor. And if we change something here, for example, I want to remove the instrumentalization from here, I need to remove it from down there as well. And I'm going to forget that. I'm going to forget that. If you're going to go back to your classes like a few months later and you have a bug here, you have identified the bug because it was very simple, or there was an output that you forgot to delete, or there was a typo in there that you needed to solve, and you go to your code and you are directly seeing the text, all right, you are fixing the text, and you're going to say your boss that you have done it, close the issue on your Jira, and then the software is going to be released with that new version, and you said, all right, I fixed the bug. And then at some point the same bug is going to occur again, because, well, it's not only used in the constructor, it's also used in the assignment down here. And this is something that I personally don't like doing. And this is something that I want to avoid. I always told you that code duplication is bad. So what I basically want to do is I want to call the destructor of my current class. And this is actually possible. You can call the destructor. The destructor is a function like any other. Nearly like any other. You can see that calling this function directly in here, directly trying to call the destructor, will not work. It's going to tell you no operator matches this operands. The problem is that this one, that the symbol from the destructor, is also an operator. It's the inversion operator. The bit inversion operator. The exclamation mark was the logical inversion, and that one is the bit inversion operator. Now, as you can see, this is not directly working. However, you can do this. And you can do this by abusing the sys pointer. If you're taking the sys pointer and then calling the destructor, this works. And if I run this works totally fine. We are manually calling the destructor, and we're going to make sure that the object is completely cleared. And this is later on going to be way better than just calling and assuming one release function is good. Because later on you're going to have things that happen, and doing this like that, make sure that everything is done correctly. Now the only thing left to do is now to actually construct this object again. How can we construct it again? Well, we could try and call the constructor. So let's try to call function precacher. Let's try to call the constructor. And this seems now like you are calling the constructor of that function. So let's try this out. And what I want to do quickly before we run this, I want to quickly verify that everything is good by actually printing out the data in here as well. So after I assigned them here, I want to quickly print them here as well so that you can see that everything works and you're going to catch all issues. And what you are seeing is nothing. Why are you seeing nothing? Normally you would now expect to get the same output that we had here again because we called print multiple times. Why don't we get this? Well, because we have an issue in our code. The issue in our code is here. There. What you are trying to do is you are trying to call the constructor. However, you are not calling the constructor on the own object. You are not calling this on the sys pointer. You are actually creating a function precacher in this single line. So actually what you got here is a function precacher that you can call compute on, a function precacher that you can call print on. And this print would actually now work. But this one is not overwriting their own data. And now you would be there and would say, all right, yeah, okay, then I'm just going to say this function precacher. And no, you are fooled. Because the language in general, it doesn't like you calling the constructor. You need to do this hacky. You need to give it the class name. If you're giving it the class name here, function precacher, this is gonna work. This is explicitly calling the constructor. By having both things, the class name and double points like the namespace and the function name. And having it like this is gonna assure that you are calling this on the correct instance. Let's try this out again. And you're gonna see that it's now gonna work. And I know, this doesn't seem very easy. And this doesn't seem more complicated. This does seem more complicated than writing your code again. But believe me, writing your code again is more pain than doing that. Way more pain. This is gonna make sure that everything gets assigned correctly. Other ones don't. Alright, so that's definitely quite some content for today. I hope you're still with me. And we're gonna do one more thing today. I'm gonna quickly show to you why you will never wanna do this without a reference. Let's make a breakpoint before we call print PC and see what's actually going on there. Right, I think you already, actually no, we don't even need breakpoints. I can fully show this to you with my printf instrumentalization. So as you can see, if I'm doing this with a copy, you can see that we have allocated that, crunching numbers, we have copied the object, and we have released two arrays. Now, this is not what we want to do. If you add a reference here, you're going to see that the code is getting way more simpler. You're going to see that you only get one allocation and one releasing. So definitely, if you can do it with references, do it. If you don't need a copy, always use references. Or pointers if it's an optional argument. But in general, use references. References are powerful. References make your code fast. If you're always going to create copies, your code is going to get slower and slower. this doesn't matter now. Now it's not really mattering because it's fast. We don't do much there. But if you're having objects like, for example, a container with 5,000 members in there, so a container with 5,000 different objects in here, and you always pass this by value for every function call, it's going to copy 5,000 objects. The C standard language is written completely fine. So if you are creating like a copy of a C++ standard container, it's going to create a copy of each of its member. So if you have 5,000 objects in here, it's going to create 5,000 copies of these objects. And there's no way of stopping this. If you have a reference, it's not going to do this because a reference is like a pointer. And a pointer is like a reference, but references are checked. And especially like for code execution, a reference doesn't cost you anything. In general, a reference is like nearly for free. A copy does cost memory and time, and that's something that we want to avoid, or that we not want to avoid, but we want to reduce. We want to reduce our computation times, and we want to reduce our memory uses. And that is why we like to use references and pointers. And that's it for today's video finally. So thank you for watching. Make sure to like and subscribe, and I'm going to remove this one off screen. Have a nice day. Until next one. Bye.